Hey, welcome to this video where we are going to talk about series circuits. What they are, what makes it a series circuit, what are the key relationships, and do an example problem where we are given some information about it and we use the relationships to solve for any of the missing pieces. Okay, first off, let's start with just the basic thing. What is a series circuit? Well, an electrical circuit is it's a path, it's a closed loop for electrons to travel, to leave a power source and return to the power source. They have to come full circle. In a series circuit, okay, as the electrons come out of the battery, the power source, this is the symbol in a schematic for our power source, like a battery. The electrons come out and they are going to travel through components that create resistance. So we're going to refer to these as our resistors, whether they would be light bulbs or the motor to something, etc. Okay, so what makes it a series circuit is that in this case there is exactly one path that the electrons follow. Okay, and that one path is a single file path. So the electrons follow each other. There's no way for them to deviate, to head in different directions, and to try to pass each other and get back to the power source by beating electrons that were in front of them. Okay, they're going to follow one path. So that is key. In case you didn't know, let's just make sure in this picture, in this first video, we define the three different properties of a circuit that we're going to talk about. They are volts, current, and resistance. Okay, voltage is symbolized by V. The subscript label is T for the total volts of this circuit, and the total volts will be your power source. Remember, voltage is like pressure. We made an analogy in class, talked about plumbing and water, and voltage is like the water pressure in the pipes. Okay, I represents current, and current is measured in amps. We'll use an A to represent our units for amps. The subscript label T is to represent the total current in the circuit. Okay, and then R is going to represent the resistance. Subscripts 1, 2, 3 will represent the amount of resistance that each resistor, each component creates in the system. R sub T is the total resistance when you put it all together of the circuit. Okay, the total resistance experienced by those electrons as they travel through. So we have some key relationships that are going to help us to figure out missing things. So based on this here, that there's one path for electrons to flow, as the electrons head out of the power source and come around, that means that the total amount of flow, okay, we think about water flowing, there's one path. We can't have a different amount of water travel through this resistor as this one. It's all going to be the same. They all follow single file through each thing. So the total current, the total flow, is the same, equal to the amount, oh gosh, writing this out, I'm not thinking. That should not be an equal sign. That should be, I'm sorry, a plus sign. That should be an equal sign. Okay, well, scratch that. Hopefully you didn't write that down. This is, I was so focused on trying to have bad handwriting when I'm writing fast, I wasn't even thinking there. All right, the current is the same, okay, through everything. The total amount of current in this circuit is all of it goes through that resistor, all of it goes to that one, and all of it goes to that one. It's the only path for it to take to get back to the power source. So they're all equal. All right, in a series circuit, the total resistance is simply the sum of all the resistors. So as we meet some resistance here, and then we meet some here, and then some here, we just add them up, and that would give us our total resistance to travel through the whole circuit. The voltage, the total amount of volts, well, the total volts is really the power source, how much pressure is created, but what happens as the electrons flow through a resistor is we get a voltage drop, kind of a drop in pressure. And the total drop in pressure has to equal the power source. Now, how much a voltage drop is across a resistor really depends on two things: how many resistors there are and how much resistance each one creates. There's kind of two things that are at play here, because the relationship is that the voltage drop across each resistor has to, in the end, sum up to equal the total. Okay, so if I had 3, I get to divide that, not necessarily equally by 3, but it gets divided amongst these 3, where if I only had 2 resistors, it's only divided by 2. If I could have the same battery, same power source, but pull one out, and then these two are going to have to pick up the difference in pressure. They're going to have different voltage drops. Okay, so just kind of keep that in mind, that it's not just based on the size of the resistor, it's based on the size of the resistor and how many resistors there are. So these are intra-relationships to point out. That means they help us understand how a variable relates to itself. So how does current relate to current? So the total current relate to how much current flows through each device or each component. And then how does resistance, total resistance, relate to the resistance of each component? And then total voltage relating to the volts of each component. So notice that each equation is using only one type of thing. As opposed to, if we move over here, interrelationships, how does volts relate to current or to resistance? We've got two equations that are going to help us out. This one here is actually called Ohm's Law. Okay, and that is that volts equals the product of current and resistance. Now I put little subscript L's just generically that you're going to have a label, just like we do over here, totals or the first component or the second. These have to be a match when you use Ohm's Law. So I made sure that's clear down here. Subscript labels must all be the same. Don't have the total volts with like the current through the first and the resistance of the second or something. These need to be all totals or all ones or all twos. Make sure we're kind of comparing apples to apples. Another formula that relates some of these to each other is the power formula. You've probably heard of watts before. Well, watts is a unit to measure power, and power is the product of the current and the resistance. I'm sorry, did I mess up again? It's the current and the volts. What am I? I'm actually under the weather today, and I can't find my whiteout, so that is a problem. Man, but you see how nice and neat I wrote? Wow, embarrassing. At least I caught it on the fly. I tried to prep and write everything before the video. Okay, so power is current times volts. So there's some key things. Remember that in a series circuit, it's one path, so all the electrons flow through each thing. That makes the current the same. It's pretty easy. The total resistance is just the sum of all the small resistors. And the total voltage drops has to equal the power source. So the total volts is just the sum of the voltage drop at the first, the voltage drop at the second, and the voltage drop at the third. On to an example. Okay, so here we have a series circuit. Total volts of 115. Total current unknown. Resistance of this resistor is 10 ohms. This resistor has a resistance of 15 ohms. And a total resistance that's unknown. The first thing you should do is just fill in what you do know. I lay this out in a kind of a table, an array. It's not exactly the way you have to do it, but I've found that this might be a nice, neat, organized way for you to do this. What I've done is I've grouped into a row all the volts, okay, so all the currents in a row, all the resistance, and I've put them in columns so that the same labels are together. So let's fill in. We know the total volts is 115. We know the resistance of the first resistor is 10 ohms. And the resistance of the second one is 15 ohms. Like that. Now, if you think of our formulas, the intra versus the inter, Okay, the intra, these are my rows. So if I look at these rows, potentially, one quick thing that I might recognize is if I have all but one value in a row, that then there's a relationship, a formula that should allow me to plug in all but the one and solve for the missing one. So the total resistance, for example, I know the two small resistors, just not the total. Well, the relationship tells me that I can add these up to get that. So this becomes 25. So the first thing I did is I used RT is equal to R1 plus R2. I'll try to keep track of the order. Okay, now the unknowns that you're presented with and the knowns you're given is going to change from problem to problem. So this is not the set algorithm for each one, but for this problem, I'll just try to document the order. All right, I don't have any of the currents right now. And the volts, I just know that these two are going to have to add up to equal that, and I don't have either one, so I'm not going to guess 115 or just make up numbers that add to 115, so I don't really know this yet. Okay, well, the next thing I can look at is the columns. The columns represent Ohm's law. Okay, and I've got my labels the same, totals, firsts, seconds. And so if I have 2 out of the 3 in a column, then I can for sure use Ohm's law. So the second thing I did is I'm going to recognize that I can do Ohm's law with my totals. The total volts is equal to the total current times the total resistance, and I have 2 out of the 3. So I can plug in the 115 and the 25 ohms, and now I can use this to find the total current. So I just divide both sides by 25. So what is 115 divided by 25? It is 4.6. So the total current is 4.6 amps. Okay. Now I can't use Ohm's law here. I can't use these. I need these. So there's got to be something else. Well, the key thing about a series circuit is that there's one path. That one path means the current through everything is the same. So once you have one current, lucky us, you have them all. So the third thing I did is I recognized that all the I's are the same, and I filled across. The fourth and the fifth things are going to be to use Ohm's law again, once with all the first components and once with the seconds, because I now have 2 out of the 3. So I can plug in the 4.6 times the 10. That's easy. That's going to be 46 volts. And here, this is 4.6 times 15. So I can do that, 4.6 times 15, and that is 69 volts. Everything is now known. I don't have any missing values. That's the goal, is to go through and figure out the total current, total resistance, total volts for the whole circuit, as well as what each of those is at each or across each component individually. Okay, so there's an example.